So eigenvalues and eigenvectors are a pair of scalar. The eigenvalue is a scalar and the eigenvector is a vector. And they have a special relationship based on a particular matrix. So we need to start off with a square matrix for this to make sense. We would have an n by n matrix, and we'll start off figuring out eigenvalues for 2 by 2s. But in general, an n by n matrix. And then there's a scalar. They call it lambda. This is your Greek letter L. And that scalar is the scale of a matrix. It's scaling a matrix, or scaling a vector. And the relationship between the eigenvalue and eigenvector is basically this equation. So this is the definition of it, is when A times x is equal to lambda times x. Now, I think that equation is worth some explanation and maybe some visual, and I think I might have a good visual of this. So let's take a look at it later, or in a few minutes. So if you have this equation where you have an equality, and you have this paired up with a scalar and a vector, the scalar lambda is called the eigenvalue, corresponding with the eigenvector x. And then the next paragraph says you have an n by n matrix, and a lambda is your eigenvalue. The collection of all eigenvectors corresponding to lambda is called the eigenspace for that particular lambda. And most of the time, well, not most of the time, almost most of the time. Does that mean some of the time? There are times where you have exactly one, most of the time, you have exactly one eigenvector for your eigenvalue. But there are a few cases where you might have more than one eigenvector for your eigenvalue. And they want to include a zero vector here to make it a subspace of Rn, because we're dealing with subspaces of Rn. All right. Before we do an example, let's take a closer look at this idea of Ax equals lambda x. And let's look at what that means. So when you take your A and then you apply a vector x to it, you get a resulting vector. So remember, if you have an n by n, and then the vector, we'll call that a column vector, an n by 1. So you have an n by n in A times an n by 1 in x, then you know that the n's, the number of columns for A has to match with the number of rows for x. And then you end up with an n by 1, which is a vector whenever you have either the column or the row to equal 1, the number of columns or the number of rows equals 1, then you know you have a vector, a row vector or a column vector. In this case, we end up with a column vector. So the result is a vector. And so what that is, or that result here, if that vector happens to be the same vector as x, except it's scaled. So x is scaled, and scaled means either stretched or shrunk but in any case, same direction. So a scalar multiple, essentially, same direction as x. So it's saying if you multiply a matrix by your x value, and you get it to be going the same direction as x, or maybe the opposite direction, but it's collinear, it's parallel. Maybe parallel would be a better word for it. So if those vectors are parallel, then you have an eigenvector. And the eigenvalue here, lambda, just tells you how much to scale it. Okay? Yeah? Well, lambda is a matrix. Do this in green. I'm sorry, A is a matrix. Lambda is just a scalar. So they're not the same. They're totally different beings. One of them is this big thing. The other one is just a number. And what they're saying is that if you apply this vector to either one, you're going to get the same value. So that's what makes it a little bit more significant. So in your textbook, I think you have pictures that kind of look like this. Kind of cool, huh? So this program here is kind of similar to the program that they have in the textbook, where they don't have a program. They just give you pictures. And what it does is that it gives you, you start off with a 2 by 2 matrix, and then it gives you a sampling of a bunch of vectors that just goes around in the circle. So it gives you a sampling of vectors, and what they're going to ask you to do, or what this program does, is that it draws what does it draw? It draws the matrix times these vectors from head to tail. I don't know if that makes sense. What's it called? Vex 2. So what it does is that these are just the black, I don't know, they look like black and red. The black vectors are the sampling of vectors, and the red vectors are what happens when I put these black vectors onto the matrix. And the matrix, by the way, is this. Let's write A. Matrix form. Uh-oh, my O doesn't work. I have this thing with my keyboard where my O, my L, and my period, and my 9, they're all along a row or along a diagonal here where it doesn't work. So I have to copy and paste the O and the L and the period. And once in a while it does that. And then if I pound on it, sometimes it begins to work. Anyways, this is my matrix. My matrix is 2, 0, 0, 3, And if I sample these vectors and I apply it to the matrix, these are what I would have. And so by looking at this, what looks like it might be a good candidate for my eigenvector? Looks like this one, right? So this vector over here, I would probably call this a vector 0, 1, this vector that's going up. If I apply that vector to this matrix, I'm going to get a new vector that's going in a slightly off direction. If I have 1, 0, I have another vector that goes down like that. So let's verify those actually using the calculation. So let's take our vector 2, 0, 0, 3. So let's say A equals 2, 0, 0, 3. And let's take a couple of those vectors that we might be able to see here. What should we call it? Let's call it x1. Oh, I'm sorry. Let's call it E1. So we talked about standard bases before we took the test, I think, and they call it E in the book. So let's just call it E1 and E2. I could have just said X, but I'm going to use a bunch of different X's. So let's just use E1 and E2 for these, and let's take a look at A E1 to see if this is going to be eventually lambda times E1. And if it is, if this is the same thing as E1 that maybe might have been scaled, then we got ourselves an eigenvector. So our A is 2, 0, 0, 3. Apply it to 1, 0. And then we get 2, the column, the row times the column, and the second one, row times the column, is 0. That looks like it works. What happened? Did I do that multiplication right? How come this wasn't an eigenvector? It doesn't have to be the same, but it should be lambda is a scalar. So according to our calculation, this is supposed to be, this looks like it's 2 times 1, 0, which is 2 times E1, which makes this into an eigenvector. But the eigenvalue would be 2, and the eigenvector would be E. But I'm not seeing that in the picture, so there's something going on here.
Their E is like sine something.
Well, it's sine and cosine, but it's just these vectors. So when I is equal to 0, I have cosine of 0, which is 1, and sine of 0, which is 0. So it should be this vector right here. But this vector goes down, the eigenvector. So I have to find out what's wrong. So I have my matrix A dotted with this. This is a row vector. Let me try something. Oh, what happened? Didn't like that. Oh, I don't know. Let's take a look at it with 1, 0. Oh wait, this looks different now. What happened? Oh, so it does work out. I don't know what that previous picture was. All right. So this is a picture that we should be looking at. So if you look at this 0, 1 vector, that's this vector over here, you can see that the eigen, or the A times 0, 1 is this vector over here that's the same direction as this, that looks like it just got stretched. If we look at this one, this looks like it's going to be the same. It looks like it got stretched too. It's a little bit longer, right? A little bit longer than this. So this is 2. This is probably going to be 3 units longer. So let's go back and do that. So we could say yes. Lambda is equal to 2 and I'm just going to start using E value and E vector. So E value with 1, 0, x equals 1, 0 as the corresponding E vector. So if we try another one, like this vector AE2, is that equal to lambda times E2? So let's do the calculations. 2, 0, 0, 3 and then 0, 1. And we'll see that's 0, 3. I'll see that it looks the same as the previous one, except this one got shifted by 3. So we can say yes again. Lambda is equal to 3. There's an e-value with e-vector x is equal to 0, 1. So it doesn't necessarily work for everything. So let's see. Let's pick another vector. Let's let x equal to, pick a vector. Any vector? 1, 1. So let's say is a times x equal to lambda times x. So let's do the calculations here. 2, 0, 0, 3 times 1, 1. And that's 2, no, yeah, 2 and 3. Now, is this 2, 3? Can I make that equal to some lambda times 1, 1? Are they scalar multiples of each other? So no such lambda can be found. To make that work. So this is not 1, 1 is not an e-vector. So we're kind of guessing and checking here, and we'll find a more systematic way of doing this. But for now, this is what we have. And with these, thank you, Daniel, for choosing this example, because that's the example that we have over here. This vector over here is 1, 1 that has a vector after you apply it to the matrix that's not collinear, not parallel. So let's take a quick picture of this and put it in our notes and identify those values. So let's see. This is our first vector, E1, 1, 0, and this is your A times E1, which is 2, 0. And you can see that that's collinear, it's parallel, so, and then the value that you get is your eigenvalue. And our second example, we got this one. This is your E2, and this vector over here is your A times E2, which is 0, 3. And we found this to be your other eigenvalue. And then our third example over here didn't work out. This is your x equals 1, 1. And this vector over here is your A times x. What was it again? 2, 3? 2, 3, which is not equal to some number times 1, 1. You can see here by the graph that this arrow slightly goes sideways. We could see that there's a couple of other vectors that worked out for us. These vectors that are going in the opposite direction, but they would have the same eigenvalue of 2 and 3. So we're really kind of focused on looking for the eigenvalues first, and then we identify the corresponding eigenvectors. Yeah?
They have to go in the same direction.
By same direction, we mean parallel direction. So if it's going the opposite direction, as long as it's exactly opposite, then we're all good. But scaled the same way. All right, so the graphics here is that I can have, for this is a simple matrix, and I had 36 before, so let's put 36 back so that we can see, you know, a lot more pictures. And if you take a look at this, you can see very slightly changing directions. And we can change the matrix. Let's see if I put a 1 over here. So that your matrix is 2, 1, 0, 3. This is still a linear transformation. Somewhere along, it looks like this is still an eigenvector because it's still going parallel. But now up on top, I don't have an eigenvalue. So, but I think there might be another one over here somewhere that's going at a slant. No, maybe not. Anyways, you can come up with really cool pictures. Make this into a -2. No, that wasn't that interesting. Anyways, here's going around the circle and trying to figure out. Let's use the same A that we had. 2, 0, 0, 3. So we can see that how that changes as we go along our sampling of vectors. And then we can have more if we want. Anyways, this is just extra fun stuff. All right. So let's get more analytic and find ways to get the eigenvalues and eigenvectors. And then we'll go back to this simple example of same example, 2, 0, 0, 3. And let's actually find the e-values. First, let's find the eigenvalues. And the idea is that you want this equation to happen for you. And the tricky part about this is that how can you solve for this equation? So we want to find the e-values lambda out of this equation. Well, these are both vectors, right? So we can vector, one vector is equal to another vector. If we bring the other vector over to the other side, we have a times x minus lambda times x is equal to 0. And these are vectors, so this 0 must be a 0 vector. So let's put an arrow on top of that just to denote it's a 0 vector. And I would like to do this, but I can't without some modification. It looks like there's a vector x being multiplied for both of them, but tell me why this wouldn't make sense. Why does this equation not make sense? it's yeah, so I have a matrix and I have a scalar. I can multiply a scalar times a matrix. I know how to do that, but I can't subtract a scalar and a matrix. So I wrote it this way, and I left a little space here because if I insert something here, that would make it work. Guess what I'm going to insert here? Identity matrix. So if I force a scalar to look like a matrix by multiplying it by the identity matrix, then that should work out. Yeah?
Is that the same as unit operation?
Almost. Remember, the identity matrix is just along the diagonal and zeros everywhere else. So it's slightly different. So this times x is equal to 0 is really looking at the null space. You're solving for the null space of this. Remember that? Solving for the null space. Any vector that you would find would fall into the null space. Null space of not just A, but a new matrix that we would have gotten A times lambda x. And so, how are we going to do this? Well, the way to do this is to find the determinant of this thing, and we're going to set the determinant equal to 0. And what happens when we do that, we're going to get a polynomial of lambda, with lambda as a variable, and then we're going to get the solve for that equal to 0. Okay? So let's do that. Let's do that using this actual matrix. So we have A minus lambda times, in this case it's a 2 by 2 matrix, so our identity is going to be I2, which is a 2 by 2 identity matrix. And when you get to do this more often, you'll know which steps to skip. There's going to be some skipping steps. You can go directly to our next equation over here, our next expression. This is going to be 2 minus lambda, 0, 0, and 3 minus lambda. So you get this far, and then you will be asked to find the determinant of this. And that is going to be just the product, 2 minus lambda times 3 minus lambda. And since the diagonals are 0, we don't have anything else beyond that. If you have something in the diagonals non-zero, then you'll have something here. You would need to multiply it out. But fortunately for us, we don't have to multiply it out. And the whole point of this is to solve for this equation when this is when this determinant is equal to 0. And the way to do this is that if you can, you factor it. And since we don't have another constant out there, we just factor this and get lambda is equal to 2 and lambda is equal to 3. So we have found two eigenvalues. Okay. So now for each of those eigenvalues, what we want to do is we want to identify an eigenspace or find a corresponding eigenvector, find one or more corresponding eigenvectors. And so that's a separate step-by-step process. In our example, we were doing things graphically. We were able to identify the eigenvectors first, and then we found eigenvalues. But in reality, you're going to be solving for eigenvectors first. You're going to be solving for eigenvalues first. And then after you find an eigenvalue, figure out what the eigenvector is, or are. Okay? So we found an eigenvalue. We found two eigenvalues, 2 and 3. And so for each of those, let's attempt to find the corresponding eigenvector. Question? You can have at most n. You can have possibly less. But you can have no more than n. In this case, we found 2. We found exactly 2. This is a 2 by 2 matrix. We could have found only one eigenvalue, but we cannot find 3. So you can have at most n eigenvalues. Well, the eigenspace will be determined by the vectors, the eigenvectors that you find. And so when they say eigenspace, we'll find the eigenspace for 2, and we'll find an eigenspace for 3, and then those are going to be your eigenspaces. So your eigenspaces correspond to your eigenvalues. Oh, well, we'll try it out and see if it makes sense after. Yeah, well, that's what each eigenspace is a line for this example. But sometimes your eigenspace could be the whole plane. Maybe. In another example. All right. So we'll keep our A. And let's find the eigenspace for lambda is equal to 2 for starters. In other words, what you're going to do is find eigenvalues, i.e., find eigenvalues corresponding to the I meant to put eigenvectors here. Find eigenvectors corresponding to the eigenvalue 2. Eigenvectors corresponding to the eigenvalue of 2. Okay, I think they call it E2. I forgot what it was, notation. They call it E whatever the lambda is, so we'll call it E2. So the eigenspace will be considered E2. Okay? So how would we do that? Well, we'll set up the same equation. AX is equal to lambda x is that famous equation now. So we'll just bring it over like we did before. AX minus lambda x equals 0. But we know lambda this time, so that's 2. AX minus 2x equals 0. And I'm doing this tediously, but again, we'll skip steps in our next example. So a minus 2I x equals 0. So let's see what that equation looks like. So we got 2, 0, 0, 3 minus 2, 0, 0, 2. This is 2 times the identity, right? Times xy, the x vector that we're looking for, is equal to 0, 0. So my new matrix here is going to be 0, 0, 0, 3 minus 1, or 3 minus 2 is 1. Right, so this is finding the homogeneous system of linear equations, except we have a super plane matrix here. So we can say, we can do the dot product here, and we'll do things a little bit differently. We have 0 times x plus 0 times y is equal to 0. That gives us no information. We have 0 times x plus y is equal to 0. So that implies that y is equal to 0. And x can be anything, right? So if we were to translate this into, I guess we should have done this using the system of linear equations way, where we have free variables and we reduce the matrix and all that stuff. I didn't do it that way. Maybe we should have done it that way. But if we would have done it, we would have called one of these as a free variable, and it turns out that x is going to end up being our free variable. So x is a free variable. And y is forced to be equal to 0. So our vector is looking like some t times 1 and 0. So x can be anything, y is equal to 0. So this is, maybe I should write that out before I write this. There's a few steps that I'm kind of skipping around here. Since we did it the way we did it, we have x can be anything, and y is equal to 0. So from here, you force it into one of those systems, x, y equal to t0, which is t times 1, 0. And there you go again. This is your eigenvector. And in this case, we have one eigenvector that spans for your eigen space for lambda is equal to 2. So E2 is equal to the span of 1, 0. So that's the eigenspace way of writing this. This is your eigenspace. But you can say that your eigenvalue and eigenvector combo, so E value, E vector, say lambda is equal to 2, and your x is equal to 1, 0. Okay, so you would do the same thing for lambda is equal to 3, and then you'll get your other, your corresponding eigenvector of 0, 1. Okay? So, back to your question, Maria. Does this kind of work out, answer the question more or less? All right, we'll do more examples if you're ready to move on. Any more questions? So the mechanics of this is pretty simple. It becomes an algebra example. Let's see, which one should we do? Let's do number 10 for an example. They gave us the eigenvalue already. Eigenvalue of 4. But let's see how to get that eigenvalue. And maybe there's 2 eigenvalues, I don't know. Maybe there's only one. So let's start off with our matrix and start from scratch. Let's pretend that this wasn't given to us. Lambda is equal to 4 was not given to us. Let's actually find it. So, after you've done this for a while, you'll be skipping steps, right? And so you'll go directly to the determinant of this minus lambda. So the diagonals will have the minus lambda, and the other parts will remain as what they were. So you see the steps that I skipped? I skipped a bunch of steps. I skipped writing the original equation, and then I just went down, and I know that I need A minus lambda I. So the diagonals, the I is just the diagonals, and lambda times I would just be lambda and the diagonals. And I'm subtracting lambda from the diagonals. Okay, so that's a big step, or a big number of steps that are skipped. Let's find the determinant. We know how to find the determinant of a 2 by 2 matrix. It's the diagonals multiplied, so minus lambda, 5 minus lambda, minus the product of the wings, that's -1 times 4. So -4, be careful with your minus signs. And so this is what I have. How does that work out? This is going to be minus 5 lambda plus 5 squared plus 4. I have a quadratic equation. If I set this equal to 0, and just for simplicity's sake, maybe if I write the lambda squared first, I might be able to think about factoring this if I can. If I can't, then you're going to have to use something else like the quadratic formula or something. But fortunately, I think this thing factors. Lambda minus 1, lambda minus 4, and here is lambda is equal to 4. That was given to you earlier. And here's another one, lambda is equal to 1. So in this case, we got 2 eigenvalues. Okay? Now, they want us to find just the eigenspace for lambda is equal to 4, so let's do that. Let's consider looking for E4 eigenspace for that. And it's going to be the exact same determinant business over here. I'm going to do this slightly differently, and I want to set up a linear equation. Well, I'll write it the way we had it earlier. So it's basically this determinant inside of the matrix of inside of the determinant here, this matrix, except lambda is equal to 4. So your modified matrix is minus 4. 4 minus 1, and then 5 minus 4 is 1, right? And it's going to be, again, I'm skipping steps. It's going to be this x is equal to 0. So when you're solving for this, remember, it's like writing that matrix as an augmented matrix with a 0 on the other side, right? It's AX is equal to B, except it's not this A, it's another A. It's A that's A minus lambda I business. So I'm just going to copy this down, and if you notice, and this should happen, that you will, if you do this, you're going to get at least one solution for this, one non-zero solution for this. And if you notice, the whole bottom wipes out, right? You can do all the row reducing that you want, and this is going to be a negative 1, a 1, 0, 0, 0, 0. Or let me just switch the signs and just do whatever matrix multiplication you can think of to do whatever you need to do. In any case, after any elementary row operations that I would do here, I get something like this, whether you have exactly this or something slightly different, doesn't matter. And what you would do is you would always be able to assign a free variable to one of these things. So I have I'll assign a free variable from the beginning. I'll say y is equal to 0, y is equal to t is your free variable. And then so we have x minus t is equal to 0, or x is equal to positive t. Positive t. So I have my xy is equal to t and t. And if I factor out a t, I get 1, 1. I can scale it any way I want. I can have 5, 5. I can have 3, 3. I can have negative 2, negative 2. But 1, 1 is the most reduced without any fractions. And so you'll see when you do this, you might want to find an appropriate or a nice vector to have your representative for your eigenspace. So your E4 is going to be equal to span of 1, 1. So is this your x? So it could be, but your x has to be has to satisfy the exact equation that we were looking at. So to make sure that it satisfies the equation, let's just double check it. We got a x equal to lambda x, and it may be exactly, it may be off by a factor of whatever t might have changed into, but let's figure out. We got 0, 4, negative 1, 5 is your a. 1, 1. Let's see if this works out. We multiply this. The first row is going to be 0 and 4. The second row is going to be negative 1 plus 5. That's 4. And so 4 times 1, 1. So that does work out. And we have an eigenvector of 1, 1 corresponding to an eigenvalue of 4. So E value, lambda is equal to 4, and the E vector, x is equal to 1, 1. Okay? Yeah.
When you have a free variable, do you know that your eigenspace is going to be a plane?
Well, in this case, since this is the one dimension, it has one vector, our eigenspace is a line. There's some cases where your eigenspace might be a plane. If you're in a 2 by 2 matrix, then it's the whole plane. If you're in a 3 by 3 matrix, then it could be a two-dimensional plane in R3. So it could happen. And we can't get to the 3 by 3 case until we study more determinants, because right now, technically, we only know how to do determinants of 2 by 2 matrices. And we'll talk about determinants of 3 by 3 matrices soon. Did we do determinants of 3 by 3 matrices here? Ronskian's not in this class. But yeah. Was it on the test? Oh. Well, that's not the same as the determinant. Was the test hard? Oh, really? On the solutions?
You're trying to figure out why it was 90 and 45.
Donovan was in that class. I took the test. Yeah, but well, that was his test when he took the class. That was last year's test. I figured that when I gave that test last year, that particular problem was kind of hard, so I decided to take it out since I included inverses on your exams and not so. All right. There are some interesting problems here. I don't know if we should do them. Let's take a look at this. Let's skip over the finite examples and take a look at this generic ABCD. Show that the eigenvalues for a 2x2 matrix are the solutions to the quadratic equation that looks like this, where TR is a trace. And so I'll define the trace in a minute. Let's take a look at that and how to show this problem. So the main idea, again, is that equation, and I'll modify the equation so that we can kind of see that matrix right away. So it's this thing equal to 0, and the determinant of A minus lambda I equal to 0. That's what we want to get at. And so what we're going to do is we're going to see, hopefully assume or be able to see that the determinant of this thing is equal to this lambda squared minus a trace of A lambda plus the determinant of A. And we'll see how that pulls out when we do the calculations. So A minus lambda I is equal to little a minus lambda b c. Remember, anything that's not in the diagonal doesn't get subtracted by lambda. Everything that is in the diagonal gets subtracted by lambda. And I want to find the determinant of this. So the determinant is A minus lambda times D minus lambda minus the wings. It's BC, CB, BC. And then here is your quadratic, except that you have to FOIL it out to make it look like, ax squared plus bx plus c business. So if we multiply this out, we get AD FOIL. We have a minus A lambda minus D lambda and plus lambda squared minus BC. So now it's just a matter of collecting your terms. I'll start off with a positive lambda squared. Now I have two terms here, the negative A and negative D. So their suggestion is to pull out a negative sign. You get A plus D lambda. That's the definition of the trace here. It's the sum of the diagonals, so trace. And then what do we have left? We have the constants left, the ones without a lambda. We have AD minus BC. Which, if you remember, is just equal to the determinant. So let's put on the side here, definition, trace. So TR of A is equal to sum of diagonals. So if you just take a look at the diagonal of a matrix, you add them all up, that's what the trace is. And that's what we got here. So this is your TR of A. This is your determinant of A. And that's it. Yeah.
Does the trace have to be reduced?
No, it should be the original matrix. And look at the trace of that. So if you start reducing it, the trace will change. All right. Questions? So let's sneak in this idea of finding the determinant of a 3 by 3 matrix. So they call this expanding on a row. And that's one way to find the determinant of a 3 by 3 matrix. And if you look at just looking at the symbols and the numbers and the subscripts, this is probably confusing. So it might be better if we take a look at it by looking at the process. And I think if we take a look at the process, it'll be a little bit clearer. So, first of all, you need to know what a 2 by 2 determinant of a 2 by 2 matrix is. That's an important part. And what I'm going to do, since I have the power to copy and paste things here easily that you were not able to do in your notes, I will copy and paste this matrix 3 times to refer to it as a matrix that we're dealing with. So, yeah.
Is there a relationship between determinant and 3 by 3 inverse?
Determinant, yeah, the relationship is a lot. It's messier than it's worth discussing. Yeah, no, it's not worth it. All right. So here's the idea. The determinant is determinant, finding the determinant along the first row. They call it expanding. Expand on row 1. And so by expanding on row 1, if you notice these numbers here, these numbers are along the first row. Now, you can expand on row 1, but you can expand on, actually, you can technically expand on any row and any column of a matrix. In this example, they're just talking about expanding on row 1. But if you see any zeros in any rows or columns, you may be interested in expanding on a row or a column with zeros in it, because that just means you have 0 times a submatrix. Beyond that, when you expand on this row 1, you need to assign a plus or a minus on your expansion. And the plus or a minus depends on where you start and where you move. So starting on the first row, this is a 1, 1. The best way to think about this in the 1, 1 situation is you add this 1 plus 1, and you take that as a power of negative 1. So negative 1 to the second power is positive. I have a 1 and a 2. You add that, you get 3. Negative 1 to the third power is negative. And so that's that sign here, negative. And here, 1 and a 3. 1 plus 3 is 4. Negative 1 to the fourth power is positive. Okay? So when you expand it, you're going to expand it, and each of the, they call this a cofactor, each of the cofactor or submatrix here will have a sign associated with it, positive or negative. So you just count from here, and then first one's positive, next one's negative, and then positive. It's alternating signs. Okay? If you expand on a different row or column, you can just think about adding their subscripts, that their position, adding their subscript, and having that a power of negative 1. That's the first thing. The next thing is when you're expanding on this first one, 1, 1, you're going to cross out the first row and the first column, and what you have left is a sub 2 by 2 matrix, and you're going to find the determinant of that. So this matrix here came from after crossing out the first row and first column. Similarly, you cross out the first row and now the second column, and you have a 2, 1, 2, 3. You have a 3, 1, 3, 3, and that submatrix that's left after you cross out the first row and second column is your 2 by 2 matrix you're going to find the determinant of. Rick?
If the number of the mirror is -5, we will not put -5 or -5?
Minus minus 5. It's negative of whatever that number is. And then the last one over here, when you cross this out, you get this 2 by 2 matrix over here. And if you've done Calc 3 and you did a cross product using the determinant of something with the ijk's up on top, it's exactly the same thing. Exactly. Yeah. Yeah, we could have done that as well. So you would get the resulting matrix here. But what you could do is you can expand on a different row or different column. Let's say my bottom row had 2 zeros in it. So I want to expand on the bottom row. So let's expand this on the bottom row. How's that going to look like? It's going to be, this is a plus, minus, plus. So I'm going to start off with a plus, A31 times the submatrix after I cross out this. So A12, A13, A22, A23. And I'm expanding on the bottom here. So this is a plus, this is a minus, this is a plus. So minus, my second one is going to be minus A32. And the submatrix after I cross that out, I have A11, A13, A21, A23, and then plus my last one, A33 times the submatrix, A11, A12, A21, A22. So what I get here is exactly the same as what I would have gotten if I would have expanded on the first row. Or I could do the same by expanding on a column. I would get the same thing. So just remember that each of these things are assigned a number or a sign, and they're all alternating. And the best way to find the sign is find its position, 2, 2. I add those, I get 4. Negative 1 to the 4th power is positive. 3, 2, I add that, I get 5. Negative 1 to the 5th power is negative. Okay? So that's how you would expand. Turns out that you could do this for any size matrix. 5 by 5 matrix get reduced to a 4 by 4, and each of those 4 by 4 matrices gets reduced to a 3 by 3, 2 by 2, and then finally you know how to find the determinant of a 2 by 2 matrix.
Does it have to be square?
It has to be square. All right, so eigenvalues, matrices. Now we can find the eigenvalues for 3 by 3 matrices and 4 by 4 matrices for that matter. All right, see you guys on Wednesday.